From high above the eastern coastline of North America, an invisible pattern emerges from the dense forests and sprawling wetlands. Hidden in plain sight along the Atlantic seaboard, hundreds of thousands of perfectly shaped, egg-like craters scar the landscape. They remain entirely imperceptible to anyone walking at ground level, cloaked by pine trees and swamp water. Yet, when viewed from the sky, a staggering alignment reveals itself. These are not random topological dips, but a vast, orchestrated geological anomaly that spans from New Jersey to Florida. Known collectively as the Carolina Bays, these mysterious elliptical depressions exhibit a breathtaking geometric precision. Ranging in size from modest, half-acre ponds to massive wetlands stretching several miles across, each formation shares an uncanny, identical orientation. Their long axes point resolutely toward the northwest, like ancient compass needles frozen in the soil. The sheer volume of these perfectly aligned, overlapping oval shapes defies the chaotic randomness usually associated with natural terrestrial processes. For centuries, the people inhabiting this coastal plain lived among these formations without ever grasping their true nature. Early farmers simply recognized them as isolated swamps or fertile peat-rich bogs, completely unaware of the broader, symmetrical geometry beneath their feet. It was not until the widespread use of aerial photography for agricultural surveys in the 20th century that the staggering reality of the landscape was finally unmasked. The sudden revelation of 500,000 synchronized ellipses instantly transformed a scattered collection of local swamps into a profound geological mystery. The sheer scale of the discovery sent shockwaves through the scientific community. Researchers were confronted with a sprawling puzzle that demanded an explanation capable of creating profound uniformity across thousands of square miles. The initial impulse was to look upward, seeking a catastrophic extraterrestrial event. Consequently, the earliest and most sensational hypothesis proposed a shower of ancient meteorite impacts. Proponents of this cosmic bombardment theory envisioned a terrifying historical epoch. They theorized that a massive comet or asteroid entered Earth's atmosphere, fracturing into millions of icy or rocky fragments before striking the Atlantic seaboard. Alternatively, some suggested a massive airburst event, where a celestial body detonated high above the glacial ice sheet to the north, sending massive chunks of ice hurtling southward. The resulting kinetic energy from these secondary impacts would have gouged out the precise, shallow craters we observe today, offering a dramatic explanation for their origin. To validate this violent origin story, investigators scoured the sandy rims of the depressions for extraterrestrial signatures. Early expeditions claimed to find magnetic anomalies and unusual soil compositions that hinted at meteoritic material. Some researchers even pointed to the presence of shocked quartz, a rare deformation of mineral crystals typically associated with the immense pressure of high-velocity impacts. For a time, the celestial strike theory dominated the public imagination, offering a thrilling narrative of planetary trauma. However, as the decades progressed and analytical techniques evolved, the foundation of the impact hypothesis began to crumble. Rigorous geological core sampling revealed a glaring absence of the expected meteoritic fragments, iridium anomalies, or the deep bedrock shattering that accompanies genuine impact craters. Furthermore, advanced radiocarbon and optical dating techniques yielded an even more devastating blow to the single-event theory. The formations were not created simultaneously. Their ages varied wildly, spanning tens of thousands of years across different epochs of the Pleistocene. With the catastrophic model faltering, geologists pivoted to a slower, more terrestrial explanation. They began investigating the complex interactions of wind and water erosion over millennia. This competing model suggests that the depressions originated as simple, irregular pools of water on a flat, sandy coastal plain. During the last ice age, the global climate was drastically different, characterized by fierce prevailing winds sweeping across a largely treeless landscape. Under these harsh glacial conditions, a process known as oriented lake development took hold. Strong, sustained southwesterly winds whipped across the shallow surface waters, generating persistent wave action. These waves systematically eroded the sandy shorelines, particularly at the ends of the pools, while simultaneously depositing sediment along the calmer sides. Over thousands of years, this relentless directional sculpting elongated the irregular pools, transforming them into the smooth, elliptical shapes oriented perpendicular to the dominant winds. The transition from a sudden cosmic catastrophe to a gradual climatic evolution represents a significant paradigm shift in our understanding of Earth's dynamic surface. It demonstrates how seemingly insignificant forces, when applied consistently over vast stretches of deep time, can engineer structures of astonishing scale and precision. The landscape is not merely a static canvas, but a highly sensitive recording device, capturing the invisible breath of ancient weather patterns in the very shape of its wetlands. Yet, the wind and water theory, while scientifically robust, does not neatly resolve every anomaly hidden within the Atlantic seaboard. Field researchers continue to grapple with perplexing variations that defy simple modeling. For instance, in certain regions, the formations are found at varying elevations, sometimes overlapping one another in complex, nested patterns that resemble a Venn diagram drawn in the sand. Reconciling how a gradual wind-driven process could cleanly overlay a new ellipse atop an older one without destroying the original rim remains a formidable challenge. Adding to the complexity is the presence of elevated sand rims that predominantly border the southeastern edges of the craters. While wind-driven sand deposition can account for some of this buildup, the sheer volume and precise stratigraphy of these rims often suggest a more chaotic, rapid accumulation. Some geologists point out that the sediment layers within these rims sometimes lack the sorting typical of gradual wind deposition, hinting that our understanding of the exact mechanism is still incomplete. Today, the scientific approach to these structures is characterized by a nuanced, multidisciplinary methodology. Modern scientists utilize advanced laser scanning technology, which strips away the vegetation digitally to reveal the bare earth with unprecedented clarity. This high-resolution mapping has exposed thousands of previously undetected degraded craters, providing a much richer dataset. Researchers now recognize that searching for a single monolithic cause may be a fundamental error in reasoning. The prevailing consensus is shifting toward a synthesis of competing scientific theories, acknowledging that multiple overlapping mechanisms are likely responsible. It is increasingly probable that the initial depressions were formed by a variety of terrestrial processes, such as the dissolving of underlying limestone or localized subsidence. Once these shallow basins held water, the relentless climate-driven wind and wave action took over, acting as a geological standardization process that sculpted diverse origins into a uniform, elliptical final product. Beyond the fierce debates over their creation, these structures hold profound ecological significance. Because they are often isolated from standard drainage networks, they have evolved into unique, ephemeral wetlands. These localized ecosystems harbor rare, endemic species of flora and fauna, including carnivorous plants and specialized amphibians that rely entirely on the seasonal flooding of the basins. The geological puzzle has inadvertently created a sprawling archipelago of biodiversity. The ongoing study of this widespread anomaly serves as a powerful testament to the scientific method itself. It highlights the necessity of remaining open to new data, the willingness to discard compelling but flawed hypotheses, and the recognition that the natural world is rarely governed by simple, isolated events. The journey from imagining fiery celestial bombardments to meticulously measuring ancient wind currents illustrates the rigorous, often unglamorous reality of geological investigation. The Carolina Bays stand as a silent, sprawling enigma etched into the eastern edge of the continent. They are a haunting reminder of the immense, invisible forces that have shaped our planet over eons. As we continue to probe their sandy depths and map their perfect curves, we are not just solving a regional puzzle but decoding the deep climatic history of the Earth itself. The true marvel lies not just in how they were formed, but in how much they still have to teach us about the complex, ever-changing face of our world.